All right, welcome back. So we just looked at the tree, we learned how to read the graph, and now we are going to test the accuracy on the training and testing set. And this is the exact same code we used for logistic regression, just using our decision tree classifier. And look what we have. The accuracy on the training data is 100%, so it completely overfit. It fit the training data perfectly. Even when our logistic regression model, even when we let it overfit, right, before we started to apply regularization, it still had an accuracy nowhere near 100. Right? I think it might have been 80. We can look back at week 4 if we'd like to see, but it wasn't 100. You can see that a decision tree really can overfit. And then the testing data accuracy is 48%, which is well under, I think the baseline, right, is around 68 or 67%. So this is classic overfitting. So now let's try to repeat the training, but let's now try to prevent overfitting. So here we are using the same code as above, right? We make our decision tree classifier. However, we are going to set the minimum samples of the leaf. We're going to try a few values. So before we do 45, let's do 10. So this means that if a split would result in a leaf with less than 10 samples, which we saw a lot of, by the way. So we go down here, look at all these leaves, right? These are all, well, not all, this one isn't less than 10, but these are all less than 10. So any split that results in samples less than 10 will not be split. So that'll just turn into a leaf itself. So we set that option. We create the tree. So now we've created a new tree. We're using the same name. So this is actually going to overwrite the old tree. We no longer, after we create this new tree, you can no longer access the old tree. So if you wanted to, you'd do a new name. But we're just going to use the same name for now. And then we fit the tree on our data, and we have the same code to create the image of the tree and test the accuracy. So let's try it now. Our minimum sample leaf is 10, and we're saving this one as DT2. First thing to note is that the accuracy on the training data came way down, and it went up on the testing data. Now, this is still an overfitting territory because testing is worse than our baseline, and the gap between training and testing is very big. But let's look at it. So I'm going to close this one. And here's the one we just made. It's smaller, right? It's definitely smaller. Let's zoom in a little bit. Training failures, going out, age. Oh, by the way, go back to the logistic regression week and look at the model that we trained on the data when we optimized regularization, and we also mean standardized the data. But we hadn't removed the students where the grade equaled 0. So remember, that was a big deal near the end of that of last week. We removed the students where the grade equaled 0 because we thought those were outliers. So if you look at the model that we trained before we removed those, right? What were the top 2 features? Failures, going out, and age. These were the 3 features that were kept in the model. Now we're applying a decision tree to the data also before we've removed the students that had a 0 grade. So those students are still in this data, right? And look at the top 3 splits. Same features. Okay, so that's always something to look at. But we're still splitting on failures, and then we split on go out and age. And if you just kind of look through here, you will see there's no box with less than 10 samples. There are some with 10, which is the minimum. So that's okay. It can go as low as 10, but it can't go lower. See that? Very nice. Okay, that is neat. Now let's try another value. So let's bump this up to 25. I'm going to keep the name of the graph the same as DT2, so it's going to overwrite that image. And we rerun this. Now look at this. The gap between our training and testing is shrinking, and the testing accuracy is actually above our baseline, right, our dummy model. So let's look at that. Ah, it's even smaller still, right? It's smaller. And it's funny, you actually have a different split. No longer splitting on age because that split resulted in leaves that would have samples below 25. So we had to go with a different split, right? The next best split that that will result in samples above our minimum. I think, and by the way, I apologize. I think previously I'd said um, if the split would result in leaves less than our minimum, that this would turn into a leaf. I didn't mean to say that. What I meant is if the split would result in leaves less than our sample, it will go to the next best split until it can find a split where the leaves are above our minimum. If it goes through all splits, right? If there's no split where the leaves will be less than our minimum, then it won't split at all. Okay, so very cool. Let's try one more. I'm gonna bump this up to 45. Let's run that. So now our testing data accuracy is actually pretty good. Of course, we shouldn't be fitting, right? You know this already because we already learned this lesson. We shouldn't really be fitting the overfitting parameters, right? This is a hyperparameter. So we shouldn't be fitting these hyperparameters on the testing set. We are basically overfitting on the testing set. So really you want to use cross-validation, and that's what we'll do next. So we'll definitely do it the right way. But this is a quick way to show the effect, right? To show this really works. It really changes the tree. So let's look at this one now. So now it was 45 was our minimum samples in the leaf. And now it's a much smaller tree, right? We have a much smaller tree. Very cool. Okay, so we've learned that overfitting is real in a tree and that it can be extreme. And we've also learned how we can use some simple parameters to prevent overfitting, although we were setting those using the test set. So now in the next video, we'll learn the right way to set this using a cross-validation loop. Very, very similar to setting regularization for logistic regression using a cross-validation loop.